welcome to Code Soul. I'm Beej. I'm organizer of Code Soul and looking forward to today's event. Today, Josiah will be doing an introduction to Rust for us. Very exciting because I also do not know Rust, so this should be very fun. There's going to be a lot of, so we expect you to have some knowledge of programming. You don't need to be an expert, but you need to know at least one language. And Josiah is going to have both some theory along with some exercises for you to do. And don't forget that you can track this online on YouTube if you want to follow along, if you're having trouble understanding things, or if you want to watch it later, it's also recorded on YouTube. If you just search for Code Soul, go to live, you'll see this video and you can look at it again later. We will also share the presentation slides and a link to the video on our Discord, which you can join right there. Oops. I might need to edit that later because we probably don't want that on the internet. Anyway. Yeah. Okay. But yeah, without further ado, thank you, Josiah, and come take the floor.
All right, hey everybody. Let me just start this slideshow here. Okay, well, let's get started. So who am I? My name's Josiah. I've worked as a backend engineer most of my career with also some experience as a blockchain engineer. I've worked at a few different companies, mostly here in Korea, that include Lunit, where I'm currently working with Beej, KidsLoop, EY, Gloucester, and Streamy. And I've been coding in Rust as a kind of hobby for the last 8 years now. So I know a little bit about Rust, so hopefully I can share some of my knowledge with you today. So yeah, disclaimer, I am not an expert as much as I would like to call myself an expert. So there may be some things that are incorrect, so just please let me know if there's anything you find that's wrong. But otherwise, I will try to share as best I can what I know. So today's agenda, so this will be divided into two parts. One will be an introduction into the Rust programming language, so some of its history, an overview of its syntax, its features, kind of how to do basic programming in Rust and some of the core ideas. And once we finish that, then we'll have kind of an interactive session where you guys can either work individually or in groups to create a Lexer, which I will explain later what that is if you're not familiar, for the Lox language, which is a cool little toy language that is kind of a companion to another book that I really like on programming languages. So we'll use Rust to build that so that you guys can not only have some introduction, but some experience building something in the language. So short history. So Rust was originally developed by an employee at Mozilla named Graydon Hoare in 2006 in his spare time as just like a hobby project. And after a few years of working on it, he shared it with the idea with his colleagues at Mozilla. And in 2009, they liked it so much that they decided to sponsor full-time development of the language. At that time, they were wanting to do some refactorings of the Firefox web browser, so it seemed like a cool idea to try to improve their development experience. In 2012, it was first released to the public, and then in 2015, it started to see adoption by major projects. The first one, I think, was Servo, which was a partnership of Mozilla and Samsung, and later on, it's been adopted by other large companies such as Netflix and Amazon and other big tech companies. Let me go back to here. Okay. So what are the goals of the Rust project language? There are three kind of main goals that Graydon Hoare had when he was first developing the language, and as the language has developed, these have remained kind of the core focus. And so that's providing strong guarantees about your code behavior, and I'll get into more detail about what that means. Focusing on ensuring memory safety by something called a borrow checker, and leveraging its powerful trait system in order to enable kind of fearless concurrency and parallelism. I'm not sure if any of you have ever tried writing parallel or concurrent code in a language like C++ or Java, but there are lots of kind of footguns and gotchas that make that experience really hard. And Rust has a very powerful system to kind of contain a lot of that complexity. So the first big thing about memory safety is that it does this as an alternative to using like a garbage collector or manual memory management. So Rust does not have a garbage collector. It also does not require you to manually free or create memory for objects. It knows when the data is accessible by its borrow checking rules, and so usually it will drop the memory once something goes out of scope. So that's the main way that like it manages memory for you, and because of those strong guarantees, it also enables some more aggressive optimizations by the compiler, which is not possible to do in other languages. So that's part of the reason why Rust has gained a lot of popularity for its performance. But I do want to dispel a few common myths and misconceptions you may have regarding Rust. So a lot of people have this kind of conception that Rust is kind of a systems programming language. Like, it certainly can do that. Like, there's nothing wrong with using Rust at the systems level, but it also has a lot of high-level abstractions that make it appropriate to use for other use cases than just systems tasks. So it has the same kind of abstractions that you might find in something like Python or C# or Java. Like, there's nothing that is not able to do outside of the systems context. Another misconception is, and this is often, you'll hear this from people who like Rust, is that if it compiles, it works. Sadly, this is not true in any language you may know, even Haskell. So, like, while Rust does eliminate many common bugs and errors that other programming languages may allow you to do, it cannot eliminate them all. So you still will always have bugs in your code. That's not going to change. But there might be fewer of them. The third one is that Rust is a hard language to use. This comes from the fact that there are a few concepts, particularly around the borrow checker, that for beginners can be a little difficult to understand. I don't think it's inherently more difficult than any other programming language. It's just that it kind of brings some of that, some of the ideas that other programming languages kind of hide from you right to the forefront at the beginning of your experience. So it can provide a smaller challenge kind of at the beginning, but I think once you understand that, I don't think there's anything that's really inherently more difficult. Finally, you'll always see a project that's been written in Rust described as being blazingly fast. There's a bit of a meme now. And while it is true that the compiler can do more aggressive optimizations, like, your choices of how you write your application are still going to dominate when it comes to performance. So your data structures, your algorithms, how you're planning on using your application, those are all going to be way more important than whatever the compiler can do for you. So I want to make sure that we kind of stay grounded in reality when we're talking about Rust. So I'm going to jump straight into kind of the overall syntax and structure of the language now. So I'm going to start with the basic project setup. So a Rust project, you will usually look something like this, where you have a cargo toml. This is similar to your package.json or your PyProject toml file. It's a kind of metadata file. B, do you have a question?
Yes.
Yeah.
Did everyone install Cargo and Rust already? Yes? Better question. Did anyone not do it? And does anyone need help doing it? Okay, I will help you. Sorry.
Sure.
I'll help you too.
Sure. Yeah, so we won't need to be doing anything just yet, but yeah, later on it'll be helpful to have Rust and Cargo installed for the interactive activity. But for most projects, you have this kind of simple, like, cargo toml file, which is your basic, project metadata file, contains information about your project. Cargo lock, which is about your dependencies. You'll have a source folder, which will include usually at least one or two files. You'll have a main.rs and a lib.rs. Main.rs is kind of the main entry point into your program if you're building a binary application. Lib.rs would be your main entry point if you were just building like a library for a data structure or something like that. So let's have a look at like an example cargo toml file. Nothing crazy going on here. You have a few sections. You can see there's a package, dependencies, and then some profiles. This is just lifted from a project on my machine, so there's nothing really special going on here. But you can see I have some dependencies listed. You can see that I have the Rust version specified. Rust does have something called editions, which are kind of opt-in feature sets for the stable version of the language. The latest is 2021. 2024 will be coming out in a few months. And then you also have the kind of build profiles. So you can have some settings for like how you want your development build to run or how your release build is run. Rust is a compiled language, so these will affect kind of the compilation process. But yeah, you can find more information about dependencies and their versions at crates.io. That's the main repository for Rust dependencies in projects. So now we're going to talk about the primitive types in Rust. So these are the basic building blocks that you will use to build all of your other complicated data types. So you have a bunch of kind of unsigned integers and signed integer types. Rust is kind of unique in that it lets you go all the way up to 128-bit numbers, which may be useful for some cryptography applications. So that's kind of a cool little feature. It also has support for kind of natively sized integers. That's what the usize and isize is. So if you're not sure if your platform, say, supports a U64, and maybe you don't actually need a U64, but you want something that just runs quickly and natively on that platform, you can use those usize or isize types. You also have the floating point types, F32, F64, Boolean values. Rust is a little bit odd in that it has 3 different kinds of like string types, and that's because strings are just really complicated. Like if you've ever looked into like the UTF-8 like specification and the code points and all that kind of stuff, so there's a lot of weirdness around strings, but the important thing is to understand is that the capital S string type is kind of your heap allocated string, so it can be arbitrary size, it doesn't really matter. The ampersand stir type is kind of more of either a string literal or a reference to a string, and char is just your single character type. So these will come into play later in our interactive session. We're going to be looking specifically at that char and capital string types. You also have a vector type. This is just like a list or container. It's a bunch of contiguous memory that's holding type T. So it's generic to any type. So those are like the main pieces. There might be a few other useful types here and there, but for the most part, these are the primitives. So how do you define a function in Rust? So it's pretty simple. There's nothing crazy going on here. So you have the fn keyword, which says you want to make a function, the function name. You give it the argument, the colon, and its type. So in this case, you can see that the argument called arg is a type U32, which is, as we saw before, an unsigned integer that's 32 bits long. You have this arrow, which is the output type, and then F32 in this case. And then you have opening and closing brackets. And then here I have just some sample lines. So this is how you print to the terminal in Rust. Use the print line macro, which is why there's the exclamation point. And then you can do kind of like, if you want to just print the value of an argument, you can put it inside those brackets like that. And so that will print the value of whatever arg is. And then at the bottom, we just have a cast. So you can cast from one primitive type to another using as. So in this case, we are just casting the U32 to float. Yes, speech.
Why is there no return?
Yeah. So you'll notice there's a semicolon after the print line and not a semicolon after the args F32. So in Rust, the semicolon suppresses the return. So if you have an expression that does not have a semicolon after it, then it will be returned. So it's like having a return statement there. You can use a return statement if you want to be very explicit, but the idiomatic way of programming in Rust is simply to have an expression that's unterminated by a semicolon to return values. Yes, speech.
I'm sorry, I'm going to have all the questions.
Yeah.
So let's say you have multiple exit points
Yeah.
from your function.
Yes.
Do Rust programmers still use this syntax, or if they have like an early return, will they use the return keyword?
Usually if you have an early return, that's also inside of like an if statement, and the if statement doesn't usually return something, so you would use the return keyword there. Usually if you have multiple return points, you'll end up using the return keyword. But if you're at the end of your function and you're ready to return, even if there are other return keywords, usually you still just use the unterminated line to return from the function.
Thank you.
Yeah, any other questions before we move on from function definitions? Okay, cool. Then let's look at variable binding. So in Rust, you use the keyword let to bind a new variable or to create a new variable. And by default, all values in Rust are immutable. So when you say let x equals 1, then you can't change the value of x later on. You can only change it if you say, I want to make this mutable with the mute keyword. So in this case, let mute y. Y is then mutable, so it can change. And then you can see you can edit y just fine. You can also do what's called like taking a reference. So you see that let z equals ampersand y. That will create a reference to the value at y. And we'll get more into kind of the rules around references in Rust, which are kind of peculiar to Rust later. But for now, this is kind of the basic variable binding structure. Another thing you can do is you can make a mutable reference. And in this case, it's noteworthy because even though y references something that is mutable, actually y doesn't need to change because it's kind of like a pointer, right? So it's still going to point to the same thing, even if you change the value that it's pointing to. So that's why you don't always need to have mute on the left side of that assignment statement if you're dealing with something like a mutable reference. The way you dereference something is using the star. So you can see star y plus equals 1. That's kind of saying dereference the value that y is pointing to, and then add 1 to it. So then when we say print line x, because y was pointing at x, and because we modified x through y, we can see that it prints 2. So does that make sense to everyone so far? Okay, cool. Let's look at data type definition or structure definition. So Rust is not an object-oriented programming language, so it does not have a concept of inheritance or classes. However, you can still define your own data types, and the way you do that is through structures, or one way you can do that is through structures. And this is how you would define a structure in Rust. So I have my struct here, and it's got 3 fields. It's got the count, which is a platform native unsigned integer. By default, fields are private unless you have the public or pub keyword in front of it, and that will let other modules access that field. Yeah, that's mostly it for structure definition as far as, yeah.
And feel free to say not now.
Yeah.
But is it common practice in Rust to use getters and setters
No.
in Java?
No. Usually, if you want something exposed, I guess if you really didn't want somebody changing the value, you could do like a getter, but that's not typically common that I've seen. I mean, it's kind of up to you. Like, no one's gonna yell at you for having a getter or a setter in your thing. Usually, if you are allowing gets and sets, you would just make the field public. If you had some kind of half visibility or half permission you wanted to give, then maybe getting a getter or a setter would make sense. But let's look at the implementing the methods of a struct. So in Rust, there is no default notion of a constructor. There's no special syntax for building a new object, or new structure. So the convention is to have a function called new, which is the thing that will create your structure. And when you are creating a struct, you can use the shorthand syntax here. So in this case, the new function, it has some arguments called count, name, or enabled. You'll notice that in the code example here, I only explicitly set count to be count twice there. Whereas for the other fields, I can use just the name and then the comma, because the name of the variable is the same as the name of the field. So that's just kind of shorthand, so you don't have to be so verbose when you're coding. And that's really common. Also the self type there, Reference is the type that's being implemented. So you'll see there's an impl my struct at the very top. So that's saying I'm implementing my struct. So when I say self, it is the same as saying my struct there. And then also one thing to note is if you create a structure outside of this kind of function, it's the same syntax. You have the name of the structure, the brackets, the fields, and the values you want. But you can only do those with public-facing fields. So it's not going to be much of an issue in our activity today, but there are some nuance around that that you might run into if you use Rust in the future. If you want to make a method for a structure, then you can just define in the implementation block a function that takes ampersand lowercase self as an argument. Similar to Python, if you have any experience with classes in Python. So if you want to reference say the name of the structure in this case, then you would do self.name. So it's pretty similar to other object-oriented programs in that respect. You can also change whether that should be mutable or not. So by default, remember, variables are immutable. So this function will not allow you to change any of the values in self. If you want to change stuff, then you would have to use the mutable syntax that we saw from here. So that ampersand mute. Okay, and then how you actually access the methods looks like this. So for instance, the new, you can see the double colon there to access the new function. So because new is not a method, it's just kind of an associated function. If you want to access that, then use the double colon. Whereas for the methods, you would use the normal dot notation. And then this code kind of does what you would expect it to do. Let's look at control flow. Well, before we look at control flow, so any questions on structure definition and implementations of structures? Okay, I'm going to move on. Let's look at control flow. So control flow in Rust is mostly what you would expect. If, else, if. That's kind of pretty common. You don't need parentheses around the conditions that you're testing for in the control flow. And yeah, the one cool thing is that you can use the control, like the if statements on the right side of an assignment. And this is where the syntax is a little bit different. So you'll notice that I still have that semicolon at the end after the if, but I don't have it after the if above. The reason for that is because I am returning the value from this if-else expression and putting that into the variable, whereas above, I'm not actually going to do anything with what might come out of that if statement. And so like each statement already has a semicolon there. So there's no reason to put a semicolon at the end of the if statement there. So yes, Pete, do you have a question?
So could you do like the let y equals before the multi-line if?
Yes.
And just add in a semicolon?
Yeah. The lines have no significance here. Rust doesn't care about your new lines. But for the sake of just fitting it on screen, I have it on one. There's also cool structures that I'm not going to cover. There's things like let else and while let, and like there are some cool syntax sugary kind of stuff that sometimes are related to control flow. I'm not going to cover those in this talk, but they do exist. But yeah, so that's basic control statement or if statement. While loops, again, what you would expect, nothing crazy going on here. You don't need parentheses, and yeah, like this code does what most of you would already expect it to do, so you just use the while keyword. For loops are a little bit different in that they operate on iterators. So you don't have like for x equals 0, x is less than 100, x plus plus, whatever. Like instead what you do is you give it an iterator to iterate over. In this case, this is called a range, the 0.100. That's the syntax for creating a range, which implements the iterator trait, which I'll talk about traits later, but basically if it can be iterated over, then you can use the for loop for it. But yeah, otherwise it's what you would expect. So yeah, I just have an example there. You would see that it starts at 0, goes up to 99, in this case, and then prints. There's also just bare loops in Rust, so you don't need to say while true if you just want an infinite loop. So the loop keyword just says loop this code forever. So sometimes that's useful if you're building like a web server application or something, you just don't ever want it to quit. So you can use loop. There also are break statements and continue statements as well. So here, like, you can break out of that loop. It's actually possible to like label your loops, which I don't really recommend just because it's like really complicated to read code that's like deeply looping and labeled. It's very loopy code. But it is actually possible if you had like multiple levels of loop to label them. But that's very, very uncommonly used in practice. Yeah, so any questions about control flow loops? Yeah, Beach.
So for loops,
Yeah.
does a loop support a condition as part of the loop syntax, or do you have to do this break thing?
You would have to use break, yeah.
Oh.
Or
So
return.
There's no for,
Yeah.
there's no while, it's just bare loop.
Yeah, just that's basically like a while true. Yeah.
And there's no alternative to a while true.
I mean, you could do while true. That like for you could like
Oh, because I'm sorry.
yeah. Yeah, there's
sorry.
while statements, yeah.
I have the memory of a goldfish.
No worries. Yeah, so like if you want to have some condition, then you can use while loop or a for loop. But then if you want something that loops forever, you can just say loop and be done with it. No need for extra syntax. Okay, another really cool feature about Rust, and this is one of my favorite parts of Rust, is that the enums types can have like other data types inside of the enum variants. Which once you are exposed to this, like you wonder why like most other languages can't do this, because it's so useful. So I know you'll probably have a lot of questions like, what does that actually mean? What does it look like? And I'll show those. But yeah, basically like the enum is kind of like a structure, except that like it's going to be one of its variants. So in this case, like I have 3 different variants, so any instance of my enum is going to be one of these 3. And if we want to like do something with the variant that it is, so you can also implement enums just like you can implement structures. So if I want to put a method on the enum that says print, if you're a struct or if you're not a struct, then this is how I would do it. So again, I'm going to break this down. So you just have the normal implementation block, just like the structures, no difference there. Again, a function definition, we can see this is a method. It takes self, so it's a method. And then we have this match statement. So because self is an enum, we know that it has to be one of those variants, right? So when we say match, we're going to say, okay, we need to like disambiguate what to do for each of the match arms, or for each of the types that this enum can be. So in this case, I have one that matches on if we are a struct type. So if you recall from the previous slide, struct is one of our types here on this enum. So if self is a struct, then S is this contained structure. So in this case, when we say s.myMethod, we're calling the my method from the structure definition that we saw before. So it doesn't have to be S, it can be anything. This is just the variable name you're giving to whatever is inside this enum. But you can do cool stuff like that. And then I have this underscore, which is just a wild card. So if you imagine that there was like 50 other variants and I didn't care what those were, I could use that wild card to match on all of them. And in this case, I just say, I'm not a struct, so this method doesn't really make sense. So yeah, Peach. I can see the hand coming up, yeah. Other people feel free to ask questions. Beach is not the only one allowed to ask questions. Yeah.
But I just want to, the syntax is completely new.
Yeah, yeah.
So I want to make sure I understand it.
Yeah.
So match is saying, we're going to check the type of self.
Yes.
And then the self struct is saying, I'm checking if self is a struct.
Yes.
And if so,
Yes.
I will store the self struct as a variable s.
Yes.
And then comma says I'm going to the next condition.
Yes, that's correct.
Okay.
Yep. So this will come in handy later in the activity today because we're going to be dealing a lot with kind of enums and matching. So it's worth understanding what this syntax means. But yeah, it doesn't have to be only self. Like you can match on any other kinds of enums if you know they're going to be applicable. But in this case, it makes sense to match on self. Also, you can do even more stuff. So the match, it's like a switch statement, right? But it's way more powerful than a switch. And the reason it's more powerful is because you can actually give any pattern you want on the left side of that fat arrow. So the kind of equal sign greater than symbol is the fat arrow. But so in this case, what I've done is say not just like match if I'm a struct, but then if I'm a struct, then I want to have enabled count and name as variables to use on the right side of the fat arrow. And in this case, I'm not using the count or the name, so I've just put underscores there to say I don't really care about those. I only care about the enabled one. But then on the right side, you can see I can say print line enabled. So this function, if self is a struct and it's enabled, then like it will print that enabled value. Otherwise, it will just say I'm not a struct. So you don't have to have like multiple matches on top of each other in order to match some complex expression. You can actually collapse them all down to one level where you can just give the pattern that you want to match on the left and then do whatever logic you need to do with that on the right. So this will not be as useful in the activity today, but I do want to expose it to you because I do think it's one of the hidden powers of match in Rust is that you're able to do this kind of matching. So for instance, if you had like a tuple, right, of like true and false, and you wanted to only do something on when they're both true, you could have a match statement on the left for like true, comma true, and then ignore the other cases. So it's very useful, and it's very nice. Yeah. Questions? I'm sure that some of you have questions, and some of you other than Beej may also be confused by what you're looking at. So I want to make sure that I can clarify any confusions. Okay, Beej, you can start us with a question.
Can you walk through it just bit by bit one more time? That was a little tough to.
Yeah. So again, what is this? What are we looking at here? So we have implementation for MyEnum. I think we all are okay with that. We have a method called print struct enabled. I think we're still okay. We have match self. So we saw before that we can match self and we can discriminate based on whether or not we're a struct, right? So that hasn't changed. The difference between this and the previous slide, right, is that in the previous slide I had S, right? And S was an instance of my struct. But as we know, right, we know that my struct has these three fields, right? So in this case we have count, name, and enabled, right? So what if I want to do something with just those fields? I don't really care about the structure as a whole. I want to destructure that into separate variables. And so that's what this syntax here is doing. It's destructuring S from the previous example, right, into three different variables, enabled, count, and name. And in this case, I'm just showing you how to ignore count and name. But otherwise, like, you would just have commas there. And then those give you, okay, now you have a variable called enabled, which reflects the value of enabled on my struct. Yes?
Is there any reason you wouldn't just... So why does this exist as opposed to just using that previous S syntax and just doing like S dot enabled or something?
Because you may not care about the rest of the structure. Like, this is a way of doing destructuring a structure in the match. So this is kind of just showing you that it's possible and how it might be useful for you.
So this isn't like an actual useful example. This is like...
In this case, not as useful because, yeah, you can just do s.enabled, but like maybe you want to like actually, propagate those values through your logic, and then you don't want it all attached or bundled together in one structure. Like, it's just a way of doing destructuring, and you can do it within the match statement itself. So, yes?
Could you match on the value of, say, enabled? So, one case where it was true and
Yes.
false.
Yep.
So
Yep.
is that more
Yes. Yeah. So I didn't want to get too complicated within one example, but yes, you can definitely match. Like if you have a number, you can also match on the value. So if it's 0, then do something, and then if it's not 0, do something else, right? So like matches are super powerful, and yeah, like you can kind of partially fill out the structure that you care about and how that might affect your logic, and have it all there. And then you don't need a bunch of like nested ifs or nested match statements to handle that. So yeah, so it's just a really neat thing, and I think it's kind of underrated. Most languages don't have this level of power when it comes to matching and destructuring at the same time. So it's just a neat feature for that is.
Another question too, right?
Yeah. Did anyone else have a question, or did it get answered by? Okay, I'm gonna move on. A couple really important enums in the Rust standard library are the option and result enums. So Rust doesn't have any kind of notion of like a null variable or undefined variable. Like a variable's always got to have a value. So if you want to represent that something may or may not be defined, you use an enum. And in this case, like you probably want the option enum. So that just has two variants. One that says, you know, there's something here. So it's the sum variant. And then you can see it contains t, so whatever it is that you want it to potentially have, or it has none. And that means in your code, like you always, like to access this inner thing, you're always going to have to do like a match or there are some methods on enums like unwrap, but like you always have to deal with the fact that like, oh, it might not be defined and my application logic has to handle it. It can't just act like it's always defined and then crash when it's not. Same goes for results. So it's very similar to the option, except it's okay and error. So again, your type could return, you know, what you were expecting it to do, or it might return an error, and then you have to handle that error, right? So
It's like Golang.
yeah, similar to Golang. I think it's a little better than Golang just because like it's more structured. It's not like a random tuple of things. Like you always know that it's gonna be either okay or error, and then yeah, you have to do it. So like for instance, in this example, maybe you have a function called register client, and maybe you have some remote server you need to connect to. So maybe you would want to connect, and connect might fail, right? Server could be down, it might not be reachable, whatever. So in this case, like maybe you need to handle both cases. So if it's okay, then you're like, all right, good, did what I wanted to do. Otherwise, there's an error. So then like I need to handle it. In this case, this also just propagates the error upward. So there's not like a really meaningful handling going on in this example. And so you could rewrite this with the question mark. The question mark just says, if there's an error, so if the previous thing returned an error, then I'm going to return an error with the inner error that I got. So it's equivalent to this code. It's just less verbose because, you know, if you always had to type out this all the time, it's kind of annoying. So this question mark kind of does that for you. It literally does exactly what this is. So you can also use question mark on option types as well, and it does the same thing. So if there is some value, the question mark will return the inner value to whatever statement you're on, or if it's none, then it will return from the function and return none. So question mark works on both the option and result enum types. So it's a super handy shortcut. It is easy to kind of like abuse the question mark in a way that like you never handle errors and you just have errors propagating all the way to the top of your application, and then like when in your main file you have like 500 different errors you might need to handle. So like I do recommend like using it sparingly or like responsibly, but it is nice to have. It's nice to know that this exists, and in a lot of cases it's like it just makes your code way easier to read, which I think is important. So yeah, questions? Yes.
So are there exceptions in Rust, or do you just use errors?
So there are no exceptions. There are panics. So panics will kind of unwind the execution stack, and so that usually involves crashing your program at some point. You're usually like, if you're wanting to write a robust application, you usually don't want to be doing panics because panics are slow and inefficient if you're going to try to use those for error handling. It is possible to recover from a panic, but I think the most common way is to just use the result types and then yeah, handle those errors as they come up. But yeah, I'm not going to cover panics just because it's a more advanced topic. But yes, like if you want to take shortcuts, you don't have to handle the error. You can just say, this is okay, or I panic. So like I think early on in your coding, that's fine, because you want things to stop when things go wrong. So I don't want to say panics are bad, but if you are trying to write like robust software, then I recommend using error handling instead. Any other questions? Okay, I'm going to move on to the next big topic, which are traits. So traits are similar to interfaces in other languages. I don't have as much experience when it comes to interfaces in other programming languages, so I won't be able to talk too much about how Rust traits are so much better. But yeah. So like but I do think there are some cool things in how the language uses these interfaces or traits to achieve some code guarantees. So I think those are unique to Rust. But yeah, so the basic syntax, you have traits, the name of the trait, and then you have the names of the functions that you want the trait to have. There's no implementation here. You can provide a default implementation, but it's not required. And then if you want to write some function that, say, requires something that implements that trait, you can use this impl trait syntax here. So in this case, greet something. We don't actually know what the type of something is. We just know that it implements the my trait. And so we can call the methods that are available from that trait. Yes, speech.
Why do you need the impl keyword? Is it possible to not use that? Would it have a different behavior?
Well, my trait is a trait, not a type. So on the right, we require some kind of type for the argument. So the impl says that like this is a type that implements my trait.
And if you put my trait, it's a compilation error?
Yes, because it's not a type.
Compiler can't figure that out?
That's just partially because there is two ways to do this. You could also use a different syntax called din my trait, or box din my trait, dyn. And the main difference is between static and dynamic dispatch when it comes to compilers. So like that's I didn't want to get into that in this talk, but that's part of the reason why. So this is using static dispatch, which is typically faster at runtime, but it does make your binaries a little bit bigger. But that's not really a concern for this topic. But yeah, so yeah, that's like the basic syntax of how you would define a trait and how you would use it in a function. So any other questions before I move on? I think this is pretty, I don't think there's anything too crazy here. Another cool thing about traits is you can make super traits, which are just compositions of other traits, right? So in this case, I've split up the previous one. So before I had 2 methods in my trait, but now let's say I want to split those up as 2 different traits. What I can do is I can say, okay, well my trait is actually just my hello trait plus my goodbye trait, right? And that is like saying, okay, I have some super trait that inherits is composed from the other traits. So the way that is used is still like the same. So like I was still like, if I want to implement the trait for my struct, I would do something like this. You say implement trait name for type name, and then I have the same methods that I had in the definitions here. And the difference with super traits is they're opt-in. So just because you implement both traits that the super trait is composed of does not actually mean that your structure implements the super trait. So you need to actually also have implement my trait for my struct. And as long as it's implemented all of the other traits that in this case my trait is composed of, then I don't need to do anything. If there's anything missing, the compiler will say, oh, you're missing an implementation for this trait in order to implement this super trait. So that's kind of cool. I like doing that. I don't know. I just think it's really interesting. I haven't really seen it in other languages very much, so it might be unique to Rust. Yeah, so questions on super traits or compositions of traits or trait implementations. Beach.
If you have two, I guess subtraits or composed traits,
Yeah.
and you try to make them into a super trait,
Uh-huh.
or you compose them into a super trait,
Uh-huh.
and the subtraits have the same method signature, is that a compilation error?
The same method signature.
let's say
So,
I have
sorry.
A say hello trait,
Yeah.
then a say hello better trait,
Uh-huh.
and they both have a say hello function
Uh-huh.
with the same signature.
Yes.
If I try to make an all hello trait, combining the two, do we get a compilation error or
No. So you can actually disambiguate those. There's a kind of a ugly syntax for doing that, but basically you would prepend your type as the trait you're trying to invoke inside of brackets, and then the method name. So like you can kind of like cast your structure to something that implements only that trait, and then access that method that way. So it's not a compilation error, but it is ugly to work with, so I don't recommend it. But
then follow up.
yes.
If you do the super trait and you don't specify the subtrait,
Then you will get a compilation error because it doesn't know which method to use.
Okay.
So you would have to disambiguate that way.
okay, thank you.
There are also a couple other kind of edge case rules around traits that are a little bit annoying sometimes. So you can only implement, here like I have this implementation of a trait for my struct. You can only do that if either the trait or the struct is defined in your project that you're working in. So I cannot implement like one trait from the standard library for another type in the standard library, not directly. And there's weird reasons for that, but basically it's like so that your dependencies don't screw up your trait implementations and everything. So there's just a few gotchas there, but for the most part that's not an issue. You can always wrap existing types with your own type and then implement the traits that way, but you just have to have either the trait or the struct in your project to do that. Any other questions? Okay. Oh yeah. Oh yeah. So that's saying that like I'm implementing the trait for this type. So this, let me go back one. So here I'm saying I'm going to basically add this method to my struct, right? So I have say goodbye or say hello, and I'm going to add that to my struct with that trait. And so then if I go back to like this impl thing, right, then it will know that this type has that implementation. Yeah.
So follow up on that then.
Yeah.
If you implement a struct with a function whose signature is the same as never mind, because you connect the struct to the trait by doing the implementation.
Yes.
Got it, okay.
Yeah, yeah. There are cases where you need to be careful if the names are the same, because if you have, say, a recursive function that's like part of a trait, but also it's like a method on your struct, then you need to disambiguate which method you're actually calling. So, those aren't going to be compile errors for the most part, but you need to be aware that like it might behave in weird ways if you're not careful. So I'm going to expose one trait from the standard library that will be useful in the activity later on, just so you've seen it before. This is the iterator trait. A lot of different types in Rust implement iterator. And this also has a little bit of new syntax. So you can see here there's an associated type with this trait called item. And then we have a method called next, which then returns an option of self item. So that item is the type of the thing that will be returned, right? And so when you're implementing iterator for a struct, you need to both provide the type for this item and the implementation for the next function. So sometimes traits can have many different associated types, and those just mean that like the implementation of the trait is going to also track those types as well. So yes.
How often do you implement your own iterator?
Um,
Because I feel like there's a lot of built-ins that would just do it for you.
Yeah, like today we're gonna we're gonna implement our own iterator, and the reason for that is kind of annoying because we need 2-character look ahead for doing our Lexer,
Yes.
and so like the built-in tools don't let you easily do that. But yeah, like for the most part you don't need to, but there are cases where you do, and today is going to be one of those cases. So that's partially why I want to expose this to you. It's also just really common in the standard library that a lot of types have this, or they'll have a method to convert into an iterator. So like for instance, the vec type, I think, has a method like toIter or intoIter that will convert it into an iterator, and then you can iterate over it. So yeah, but yeah, it's a really useful trait to know about. Also, I'm gonna just kind of expose you, or we're not gonna go into a lot of detail with these, but these are kind of the most important traits in the Rust system. So first are copy and clone. So copy is kind of like a shallow copy of an object. So if it's something that can kind of live in the stack, like many objects of this can live in the stack, usually they'll implement copy. So that's something to be aware of. Clone is like deep copy. So if you have some long string and you want to duplicate it, you can call clone. Most objects also implement clone. Debug and display, these just kind of control how things are printed to the console. And so they're just 2 different modes. So when you print a line, like it normally uses the display implementation, but if you add like a colon question mark in the print line, then like it can change it to debug mode and it will use the debug representation. Equal, partial equal, OR, and impartial OR, those all control kind of like how to order objects in some collection. And then we have from and into. So if you want to convert between data types, then the from and into traits control that implementation. Then there are the last 3 are a little bit special. They're called auto types. So these are traits that all structures automatically implement when you define them, unless you opt out of them. So you don't need to say that like something is sized or send or sync. That's kind of automatically assumed. And then if one of the members of a structure doesn't implement one of these, then it will exclude itself from that implementation. So size says that this is a fixed sized object, so it's not some arbitrarily sized thing that we don't know. Send is saying that we can safely move this data between threads. Sync is that we can safely share the data between threads. The distinction being that moving means it's not available on the other thread once it's been moved, whereas shared is both threads could access that. So those are the most common and most important traits to know about, I think. I may have missed 1 or 2, but for the most part, I think that's the case. Any questions on those? Okay. Then the last thing I want to talk about with traits is you can also kind of use this derive macro, which is an attribute procedural macro. I'm not going to talk about those, but basically like you don't have to always do impl clone for type or impl debug for type if it's kind of an obvious implementation. So some traits have this derive macro. So for instance, derive clone means that if all of the members of my struct implement clone, then my struct also implements clone. So it kind of generates that implementation for you. Same with debug and a bunch of other different traits. So the derive window is just handy to reduce the amount of boilerplate that you have in your code. Yeah, okay, so that's traits. Now that's kind of a lot, and it's probably there will be parts that will come up later in the activity that maybe will be worth revisiting if those are confusing. Okay, modules and imports. This is pretty simple. So to declare a module, you use the mod keyword. So in this case, my module says there is a file called my module, and I'm going to make it a module available in my application. You can also do mod name and then open and closing brackets if you want to have a module that's like inside of a file and only available inside that file. You'll see it in the tests later. It makes more sense there. You can also use the super keyword to access the parent module of the module you're currently in. It also supports glob imports like Python, so you can import everything from a module. You can use the create keyword to reference the root of your currently working crate. And then, yeah, for like other dependencies and stuff, you just use the name of the crate, and you can use the double colons to traverse the module tree. Yes, Beach.
What's a crate, Josiah?
Crate is just the name of your Rust project or a Rust project. It's technically the unit of compilation in Rust, but yeah, for the most part, it's going to be whatever project you're working in or whatever projects you import. So, yep. Then, so unit tests in Rust are nice. They're pretty easy. So you have this little attribute at the top saying that this is in testing, so only compile this when I'm testing, basically is what that CFG test means. You can see the mod test, so I'm making a module called test in this file, which is why I'm using the open and close brackets. One special thing about unit tests in Rust is when you define unit tests like this, you have access to the private members of whatever's in this file.
Oh.
Yeah, so if you have some structure with a bunch of private methods and private members, you can access those directly as if they were public inside of the unit tests, but only inside of the unit tests for that file. So it makes testing stuff really easy. You don't have to like bend over backwards with visibility in order to make those tests. And then usually I just import whatever is in the parent module. So in this case, we're inside that module test. So I need to go up one to get to the file that I'm trying to test, and then just import everything from there. You annotate each test function with the test attribute, and then inside you usually use some of the assert macros to do your tests for whatever they are. There's a bunch of different assert macros. I'm just showing one here. But yeah, it's all built in. You don't need to use like a testing library to run tests in Rust. So that's really nice. Questions?
I have two.
Yeah.
So you mentioned basically ignoring private modifiers or whatever. What triggers that? Is it the CFG test, or does the module have to be named test, or how does it know when to do that?
That's a good question. I'm not entirely sure how Rust knows. I suspect there's probably some special casing when it comes to the module that CFG tests when it's doing the compilation. I don't know exactly how the compiler knows to like what logic is responsible for allowing you to access that information. Yeah.
And then this test module that you have an example, does it have to be named test, or could you do like unit test, integration test? this kind of thing?
I don't know off the top of my head because I've never thought to change it. You could experiment with it and see. I suspect it probably doesn't matter. I think that CFG test probably does most of the heavy lifting for you, but yeah, feel free to test it and let me know.
Okay. And I have a third question.
Yeah.
Sorry. Is there mocking built in?
No, there is not mocking built in. So if you are judicious in how you use traits, then you can use traits to create mocks pretty easily. So it's really encouraged to use traits in your code. You don't have to. Obviously, you can write an entire application that has no trait definitions whatsoever. But the reason that traits are really useful is that then you, in your tests, right, you can just make a simple mock structure that implements all the traits that your normal application would have, and then edit its behavior to suit the needs of your test. So I encourage you to experiment and try writing traits and using them quite frequently in your code. I think people often don't write enough traits in their Rust code. Any other questions? You also can use kind of semi-integration tests. So if you want to do tests where you don't have access to the private members, you can make a folder next to your source directory called tests, and Rust will treat those as kind of your public crate tests. So it will import your whole crate, and then you will only have access to the public members of your crate when you run those tests. So if you want to do kind of semi-integration like tests, you can do those in there. And they work very much, they're still defined very much the same ways here, but they're just in that different location. Okay, so we talked a lot about the basic syntax of Rust. I've covered most of everything, so you could probably now, if you just stopped listening right now and started coding, you could probably code some simple applications in Rust without too much trouble. But there is one concept that you will be missing and that will definitely bite you and that is the borrow checker in Rust. So this is part of the reason that why Rust has gained a lot of popularity and why it's so different and has the reputation that it has. So I'm showing you some code here. This code does not compile. Can anyone tell me why? Someone other than Beach. Right, it looks fine, right? It doesn't look crazy. Okay, Beach, do you wanna wager a guess?
It's been a while since I've done C-like stuff, but it looks like you're trying to increment the reference of y.
So actually, that's not the problem.
Okay.
So you'll notice we've seen an example like this from before when we were talking about variable binding. The only difference is I added the extra line at the bottom. So without that line at the bottom, this would compile no problem. So yeah, I'm not gonna embarrass you guys for too much longer. So the reason has to do with something called the borrow checker. So here's the compile error that you would get. I know it's a little bit small, so you might want to come back and read this. So the compiler will tell you that there's a mutable borrow, and then that there's another immutable borrow, and then there's a mutable borrow used later. What does all this mean? It's kind of nice that we have highlighting and showing you exactly where these variables are conflicting with each other, but we don't really understand the concept of why this is a problem, right? So before we can really understand this, we need to look at the kind of concepts of ownership and borrowing in Rust. So I'm going to start with ownership. So what is ownership? Basically, there are three rules. Each value has an owner. There can only be one owner of a value at any given time. And when the owner goes out of scope, the memory is dropped or freed. And if you transfer ownership between two variables, that's called a move. So you cannot alias variables in Rust. So you can't have two variables that are independent that point to the same thing, because that would mean that there is more than one owner. So that's the first kind of piece of this puzzle is ownership and these rules. The compiler is always going to be checking these rules, so it's important that you know that they exist. So here's some examples to kind of illustrate some of ownership. So we have let x equal some string value. So x is the owner of the value, a string value, right? If I say let y equals x, I move or transfer ownership from x to y. So if I try to print x in the next line, that's going to be an error because x is gone at this point because it's transferred ownership over to y, so it can no longer exist. Then if I pass y directly into some function, the function becomes the owner of y. So then on the next line, if I try to access y, y is gone because it's been transferred into that function. So that function might do something with it, but after that function ends, y is gone. So it's kind of really, I think these examples kind of really show some of the more stark implications that the ownership concept has. So it's really important to understand what's going on. Yes, speech.
So, what if you have a struct and you want to assign a value in that struct to some other variable? What happens? Is the whole struct gone?
No,
or?
so that you can have partial moves. So, but at that point, the struct as a whole is kind of in the process of being split up. So if I have three fields on my struct and I do let x equals field 1, then field 1 is gone from that struct. So you can never access my struct dot that field anymore because it's been moved into x, right? So
That seems very difficult to keep track of.
Well, it's not as bad as you would think because this is not the only way to handle variables. Remember, we have references. So we're going to get into how to avoid this for the most part in the next part. But yeah, if we didn't have references, right, then writing code in Rust would be awful because this would be really difficult to always be keeping track of.
But you were just saying that two variables can't reference the same value.
No. They can't own the same value.
Oh shit.
So yeah, everything here. This is talking not about references. This is talking about ownership.
A completely new concept.
Yeah. So this is new-ish to Rust. I don't think it's the only language that has it, but it's the most popular one that does by far. And so yeah, when we're talking about ownership, like we're talking about when this variable is gone, the memory that it owns is also gone. So that's pretty significant. That's like how we avoid having a garbage collector in Rust, is because of this rule, right? Because of this concept of ownership. That's how the compiler can guarantee no one else is using this anymore. Like, I am free to delete this and reclaim this memory. So, however, I'm going to throw one little wrench into this concept. This code, which looks identical to kind of what we had here, right? It's very similar. This will compile just fine.
I have a guess. That's the one else first.
Yeah.
Mutable and immutable variables are regarded as different.
So that's a good guess. It's not right.
Well,
It-
someone else?
Oh, no.
So I don't know if what I'm going to say is the same as what he said or not.
Uh-huh.
But because y is mutable and it's being set to x, to me that would imply a copy.
Okay, so it has nothing to do with mutability. It has everything to do with what you just said, the last word you said, copy.
Yeah.
So in this case, the only difference between this example and
As the
Well,
reference of x.
well, here is a little bit, it's actually even a little bit different from copy. Here it's because there's a reference, but like if we look at the string example here, right? Like the reason these fail is because of copy. So if you have something that implements copy, then what actually happens when y equals x is it says copy the value that's at x and give it to y. It's not doing a move in this case because the value, 1 in this case, implements copy. Because copies are like kind of very cheap. Like they're kind of very inexpensive to perform when you're talking about small data structures like an integer or something. And so the compiler says that like, okay, like you implement copy, so if you are trying to, do this y equals x thing, then I'm just going to copy it for you. I'm not going to move it. Yes?
Can I force a move? Can I write something to insist that the memory location is moved rather than being copied?
Can you force a move? I mean, the thing is a move is equivalent to a copy. Like, when you do a move, so for instance here, what's happening is that the pointer address that is currently, at x is being copied to y, right? But then because Rust does not let you have multiple ownership of the same data, it's going to then delete x from the compiler, right? So like what's happening here is actually similar, but what is different is that because the value is so small, Rust says, well, I don't need to worry about multiple ownership because everything here is small, so I can just copy x to y and then let you have both variables, right? But they're not going to change in tandem, right? Like this y plus equals 1, when you print x, x is still 1, y is 2.
So what if it's not an integer but like a big struct that Rust says, okay,
So then in that case, when you do just this simple let y equals x, if x doesn't implement copy, it's going to move. So, yeah.
So you made an implicit implication here.
Yeah.
1 is an integer.
Yes.
And 1 has copy.
Yes.
This is a string, and string does not have copy.
String does not have copy.
And that's why
Yeah.
this is a move, but the other one is a copy.
Yes.
Okay.
Yes.
But I'm sorry, you didn't finish answering his question. I think, so.
Oh, I think I did. But yeah. But yeah, like
Please. Because it was confusing because I was like, oh, the mutability is doing it, but it has nothing to do with the mutability.
No, yeah, it's nothing to do with mutability. It's all to do with whether or not a type implements copy. In this case, yeah, a string does not implement copy because a string could be arbitrarily large. There's no hard limit on how big a string is. So if you have some big string, it's probably being stored in the heap somewhere, and then it can be as big as you need it to be. So yeah, like the data type doesn't differentiate whether or not it's in the stack or in the heap. It just kind of assumes it's in the heap. So yeah, that's like the major wrench in this scheme is like the copy trait will change that behavior. So you can't always expect this kind of move semantics to happen when you're dealing with relatively small data types or data types that implement copy. Yes?
So how can you tell which operation is a move and which operation is a copy?
So you need to look at the struct. Like you need to look at the type to see if it implements copy or not.
So it all comes down to types?
Yes.
Okay.
So it's going to depend on, you know, what implementations does that type have? Does it implement copy? If you're working purely in kind of generic land where you don't really know what your types are, then your bounds on the types are going to tell you whether it's copy or not, because it will not assume that it implements copy, right? You'll have to put that as a bound on your function, so you'll know. Yeah.
So, since, like, when you reassign the values
Mm-hmm.
for some of this, like x and y,
Yeah.
since it's no longer accessible, is it possible for you to reassign something else to the values?
Yes. Yeah. And in fact, even if it is still accessible, you can do another let x equals something else, and that will just redefine the variable and drop it. Yeah.
But I imagine that would be bad practice for readability.
I would not recommend it. Yeah. Yes.
So the compiler can determine if it's error or not.
Yes.
It means the so we called move function
Mm-hmm.
is move function have to be implemented in code, not dynamically on runtime.
Yes. Yes, that's correct. Yeah. Like at runtime, everything has to be figured out already. Like either that or there needs to be a structure for figuring it out at runtime. Like I mentioned before with dynamic dispatch, and that's a more complicated topic I'm not going to get into. But for the most part, yes, that's correct. Everything needs to be pretty much spelled out at compile time. Yeah. Okay. Any other questions? Yes.
And just to summarize to make sure at least I understand.
Mm-hmm.
Move is the default. Copy happens if the data type implements copy.
That's correct. Yep. So
And it all happens at compile time, so if we messed up between move and copy, we'll get a compilation error.
That's correct.
Okay.
Yep. Yeah, usually you'll have some error similar to kind of what we saw here about, you know, stuff not being available when you thought it was. Okay, so that's ownership. Now let's talk about borrows. So before, remember that like with just ownership, right, like this could cause a lot of issues with like, oh, now I gotta like not, you know, have multiple references to something, but like it's not actually true because borrows let us kind of relax this restriction a little bit. So a borrow here is just the ampersand, right? Whenever we use ampersand, we're creating a reference which is borrowing the value from the owner. Yes, speech.
Does anyone not know what an ampersand is?
Ampersand is the symbol in front of mute. So that's the kind of and sign. English is called ampersand. English is weird. But yeah, so that symbol creates a reference. A reference borrows data from an owner. So I want to make that vocabulary very clear when I'm talking about all these things. This does not create a borrow. Borrow is a verb. It borrows from the owner, and it is a reference. It's not a pointer, it's a reference. Reference has the special rules attached to it versus a pointer which doesn't. So here we are creating like a mutable borrow reference in y, and so then we can do stuff, interact with y as if it was similar to x, right? And it's going to change the underlying data that x owns, right? So this is like kind of what you might have expected in other languages this code to do. But in this case, we are being very explicit about the fact that we are borrowing from X. So even if X implements copy, we're not going to do any copying here because we are explicitly saying, I want to reference this value, right? And I'm not trying to create another duplicate of it. I'm just trying to create a reference to it. Yes, Beach?
What happens if you don't have the star in front of Y?
Then you'll get a type error because Y is a reference. And yeah.
So once you create a reference variable, you have to be like, this is a reference.
Yes, and if you want to do something with the data type it's referring to, you must dereference it.
So that's kind of to guard you from like accidentally updating a reference and changing values where you don't expect.
Yeah, like in C, you can do like pointer arithmetic, right? So this is saying, looks like you're trying to do pointer arithmetic. We don't do that in Rust. So like, that's yeah, you had a question.
Yeah, so if I drop the mute
Yes.
behind an ampersand, is that a mutable borrow, and does that affect the runtime of?
Oh yeah, so that would become an immutable borrow, and that would then not let you do the next line, which edits Y. So I have star Y, so I'm dereferencing Y and then editing it. So if you remove the mute, then you would get a compiler error saying that like Y is not mutable, so like, and it's not pointing to anything mutable, so you cannot. What's that?
Can I print Y?
Oh yeah, you can
So
print
I can
Y.
print Y. It's a mutable borrow.
Yes. Yeah.
I'm a little excited and I don't know why. So X is mutable.
Yeah.
Right?
Uh-huh.
I can make an immutable reference to X.
Yes.
And then if I change X, Y will be updated, but then Y can't update X.
Well, you
No?
can't change X while you borrow it immutably.
While you borrow.
Yes.
What does that mean?
While there is a reference that is an immutable borrow.
So you have to kill off Y before you could change X.
Yes. So I'm gonna go over the rules here, so that will clarify things. So there are kind of 5 main rules regarding references in Rust, depending on how you want to count them. So here are just the basic borrow checking rules, and they're simple, but they come up and manifest in a lot of different ways in your code. So understanding these rules is really worth it because, like, if you have a misconception of some of these rules, then like you're going to try to do things that you just can't do. So first is that a value may have any number of immutable references, right? It doesn't really matter how many. An immutable value may not have any mutable references, right? Oh, sorry. No. Sorry, this is really annoying.
Keep going.
Okay, anyway. So a mutable value may have at most 1 mutable reference. And a mutable value may not be modified when there is at least 1 immutable reference. And finally, a reference must always be valid. That last rule is related to the lifetime. So remember, with ownership, when something goes out of scope, the memory is freed. So you can never have a reference to something that could be freed at some point. So that's why that last rule is there. Yeah. So those are the 5 kind of main rules around references. So in our example from before, we had, let me go back here. So which rule did we violate, right? Like in this case, right? Well, we have a, let me go back. Hold on, check my notes to be sure. Beej, you're very distracting.
I'm sorry. I'm sorry, guys. I can't fix the buzzing.
So.
That is really annoying.
So yeah, so the issue with our code was that basically we had, if you look at the compile error here, right? Print line x creates an immutable borrow of the value of x, which means that we can't still have a mutable reference to x. You can't have both an immutable and a mutable reference at the same time. So that's why our compile error was happening. So like these kinds of things, I guarantee you will run into. You will violate these rules while coding, and then you will get a bunch of compile errors. And so it's really worth understanding like what these rules are and how they can be kind of coming out of very deeply complex structures that you may have. Like you may not realize that you're trying to violate one of these rules, but usually you are. So this is the main point of like difficulty when it comes to coding in Rust, is trying to understand how you are violating these and how you can avoid violating these. So yeah, questions on ownership and borrowing? Beach.
From a usability perspective, I understand why you can only have one mutable reference to a mutable value.
Mm-hmm.
Is usability the only reason, or basically why does that rule exist?
It exists because Rust is trying to make it impossible to have data races. So if you have two mutable references to the same underlying data, and they're running, say, in different threads, right, then you can't be sure what the value underneath is. Because in your code for thread 1, you might make some modifications and assume that it's 1 bigger because you just added 1 to it. But then in your other thread, if you have a mutable reference, then you might make some other modification based on what you read from it before, right? And so like these rules make data races impossible. So that's like a really big win for like doing asynchronous or concurrent and parallel stuff, is making that impossible to ever happen.
So then, but then why doesn't that problem still exist when you have one mutable reference?
No, because it can only be changed by that one reference. And that reference can only ever live inside of one thread.
So then because I'm imagining a scenario where you have the ownership variable, then you create a mutable reference, and then you have these running in two different threads.
So the mutable reference can't be duplicated, right? Like, because then you would violate the rule. You'd have more than one mutable reference.
Oh, so the original owning value is a mutable reference? No, because you did Y was a mutable reference. So.
I'm sorry, maybe I don't understand the example.
So let's, going back to X and Y.
Yeah.
Okay.
So
let's say X is in my main thread.
Yeah.
I do some passing or whatever to create mutable reference Y.
Yes.
In a different thread.
Uh-huh.
Don't I have the same problem of two variables being able to modify the same value?
No, because you won't be able to like modify X here anymore. Like once you have that mutable reference, then that's the only place that can edit that value.
Okay, so basically when you create the mutable reference,
yeah,
the original owning value cannot change the value until...
Like you can't really do anything with X until Y is gone.
Okay, so then if we go back to the rules...
Yeah.
Then it sounds like rule 4 is not only for immutable references, but also for mutable references.
Yeah, I guess that's also true. Yeah.
Okay.
Yeah.
So a mutable value may not be modified when there's any reference.
Yes. Yeah.
Okay.
Like it can only be modified by the mutable reference.
Got it.
Yeah.
Okay.
Yeah.
So for concurrent applications, like in C++, we have multiple threads having shared memory, sharing some shared pointer or something.
Yeah.
So is that possible in Rust?
So, well, you would need to use some like synchronization structure. So like a mutex or.
So mutex, I'm guessing, would allow you to like transfer ownership.
So in that case, what would happen is the mutex can guarantee that only one thread is able to access the value at a given time, right? So then it would have some implementation so that when you access the mutex, then it only creates mutable reference to that inner data for that one thing. So it can convince the compiler that these rules are still being upheld, right? But in your application code, you can have references to that mutex, right? Usually they use something called like a reference counter or an atomic reference counter to control access to the mutex, and that lets you kind of get around this rule, at least from a usability perspective. But then you still have to worry about the fact that like you have potential contention between those threads accessing that shared data, right? But what this means is that you're never going to have to worry about like the value changing underneath you while you're trying to do something with it. So, yeah. Any other questions? And you guys are experts at borrowing. No question. This is like the biggest, most challenging part of Rust. And you guys, all right. I'm going to trust you guys are the smartest Rust developers I've ever seen. So the exercise should be no problem. Okay, so that's like basically all of the theory that I'm going to cover today, or at least during the talk. So when should you use Rust? Like what is it really ready for? I would say pretty much whatever you want. There are a few rough edges, so I want to warn you about them so you don't like go off into the areas that I think are tougher to use Rust in. So Rust doesn't have like a stable application binary interface, ABI. So what that means is that you can't create like shared library objects like you might do in C or C++, and reuse those across different projects. Like you can have those, but like you have to go through the C ABI to do it, which means you lose all of the like safety guarantees that the Rust compiler gives you. So it's like when you interact with C ABI objects, then you have to assume they're unsafe. And Rust does have an unsafe mode of operation, but I'm not going to cover it today because I think it's a little bit too much. There's like with unsafe Rust, you can kind of disable some of the borrow checking because you're saying, hey compiler, trust me, I'm still upholding these rules, right? We all know that's a lie, right? But because Rust is gonna assume that when you write unsafe code that you are upholding those things, then you have to be really careful about like, what if the compiler decides to drop this value because, in normal situations that would be okay, but then your unsafe code is buggy and then it causes, errors. So like, I'm not going to talk too much about unsafe code, but like when you're dealing with other programming languages, you will have to interact with unsafe Rust because the compiler cannot guarantee that these objects that you're trying to import and interact with actually uphold the same guarantees the Rust compiler has. Even if it's like two different versions of Rust, right? Like it can never really know that like the previous version of Rust is going to still uphold whatever things the new version of Rust does. So there's no stable ABI yet. It is kind of being talked about, but for the moment, I would say like if you're dealing with like OS kernel stuff, or like you have a bunch of C dependencies in your project, Rust might not be the best choice just because of like the extra boilerplate you'll have to go through that unsafe kind of barrier with the other code. The other area that's a little bit rough, this is not as bad, is with async code. So Rust does have syntax for dealing with async code, but it doesn't ship with any kind of async runtime by default. So you either have to build your own runtime or import an existing one from the community. There are a few popular ones like Tokyo and Small. Those are two popular async runtimes, but like it's kind of a little bit lacking. Some of the traits as well are a bit more restricted in the kind of complex type stuff you can do when you're defining traits that are async. So there are a few limitations when it comes to writing async Rust. If you're just going to build like a web server, I wouldn't worry about it. Like this is totally fine. You can just use Tokyo or Axum and then spin up a web server with very little difficulty. So I don't want to discourage you from using Rust in a web backend sense. But if you're doing like advanced parallel async stuff, then like it's a more complicated area than what I've shown you so far. So I just want to make sure that you guys are aware, so you don't immediately take this talk and then go straight into one of these a little bit rougher areas and have a hard time. So yeah, any questions overall on the kind of basic Rust introduction? Anything I haven't covered or areas you might be curious about? Yeah.
I found another reference. You can't modify a value while it's borrowed.
Okay, yeah. Good to know. Can't modify values while they're borrowed. Okay, well, if there's no questions, again, and you guys are the smartest Rust newbies I've ever seen, then let's test your knowledge and build a Lexer. So I'm going to shift to the interactive section of the session now. So this is going to be, I'm going to set up the problem, I'm going to give you a starter repo template to work with, so you don't have to start totally from scratch. But it's going to be mostly up to you to finish the implementation for this. So that's kind of the outline. So what is a Lexer? So a Lexer is part of a compiler that basically reads like character strings. So if you have some file of text, then you read the text's characters and then convert those into kind of more meaningful tokens that then later the compiler can parse and deal with. So we're going to build a Lexer for a language called Lox, which is just a toy language made by Robert Nystrom. It's featured in his book Crafting Interpreters. That book is available for free online. So if you want to learn more about compiler development or interpreter development, then I highly recommend this book. But for the purpose of the exercise, you can basically think of a Lexer as an iterator that produces tokens as output. So I have an example at the bottom here. So if we have the text characters, x equals 1 semicolon, we're going to convert that into identifier equal number semicolon into file. So we're just taking one representation of data and converting it to another. So we're just going to implement an iterator to do this. So I'm just showing you this for completeness. It's not all going to be relevant for exercise. This is kind of the grammar for the Lox language. The most important bits are at the bottom, where you have number string, the Boolean literals, a nil literal, some parentheses, so on. And so this is just for the purpose of completeness. I do not expect you to understand most of this. It's just how the language is defined, and so if there's any ambiguity when you're doing the exercise, it might be helpful to understand. So yeah, I have a link in the slides. You can go to my GitHub profile. There is a repo here, Code Soul Rust Intro, and you're free to work individually or in groups. So yeah, now is the time to clone the repo, download it, decide who you may want to work with to do this. I am not going to hold your hand through it. We can take a look at the repo structure, so I can give you a quick introduction to it. It's very simple, but yeah, you're free to ask for help or guidance. But I really want to let this be an opportunity for you to put all the stuff that I just talked about to the test to see how much you can remember. And yeah, it's a bit of a challenge, so don't be discouraged if you can't figure it out, or if you have trouble, I can help you. But yeah, let's go ahead and I'm going to close the presentation real quick, and I'm going to open up the repo so that you guys can have a brief introduction. If you look at the Code Soul Rust intro, so it's basically just there's yeah. Let me know if you guys can access it. It should be public, but can you see it, Beach?
Yeah.
Okay.
Just think
Okay. Just want to make sure there's no problems.
Yep.
Yeah. Okay. So I'm just going to go over the quick structure of this. Again, I have a restatement of the problem in the README. So this is, again, if you recall from the beginning of my talk, I went over basic structure. So we've got our cargo toml, cargo lock. You won't need to import any dependencies to complete this exercise. Everything you have is already there. So if we look at the source directory here, there's just 4 files. There's Lexer, lib.rs, main.rs, token. Most of the work you're going to do is in this lexer.rs file. And so this has kind of a skeleton for you already. So we have a structure called Lexer. It's got 3 fields: line, source, current index. And we have some helper functions here to basically go over the characters. So this will read in a string, and then it will iterate over the characters of the string. So we've got some helper functions for you here. And then your main task is going to be to implement these functions. So how to identify an identifier, a keyword, a number, or a string, and the next method for the iterator. So Is any part of the problem description unclear? I want to make sure that like nobody's confused about what they actually need to do. So remember, we need to take in tokens and then or characters, and then convert them into these tokens, which I've already defined for you in the token thing. So we have the type of the tokens. There's a bunch of different characters that we might encounter or keywords, and then also we want to store, like, create these token structs which have the type of the token, and then the lexeme is just like the actual string characters that represent that token, and then which line that they're on. One thing that can help you is I have unit tests included in this project. So if you go towards the bottom of the file, you'll notice a bunch of unit tests here. These will help show you kind of what your output needs to be. So for instance, like here we're saying, like, if you just have an empty string, then you should return the end of file token, right? Like, that's the only thing that would be meaningful for the compiler in that sense. And so you can run these tests with cargo test once you've cloned the project, and then it will show you which ones pass, which ones fail. If they fail, it'll tell you, you know, what your output was and what it should be. So yeah, like that's the exercise. It's not meant to be super easy. It's also not meant to be that hard. The actual amount of code to get this to work is fairly small, but it's going to require a little bit of thinking. So yeah, have at it.
You're gonna help us, right?
Yeah. But you got to ask for help if you want help.
Yeah.
But I do encourage you to spend a few minutes to like think about it a little bit before asking for help. But yeah. And then I'm gonna stop the YouTube stream, Beach. Is that okay?
Is one second.
Okay, sure.
So first off, do you have a solution somewhere?
Yes.
Okay. Can you tell the stream where the solution is?
Yeah, the solution is on my other repo, Lockside, on my GitHub profile. So same profile, just different project.
Okay.
It's
What's the name of the project again?
Lockside, Loxide.
Loxide?
Yeah.
Okay.
It's in the scanner.rs file.
Okay. Cool. All right. So, right. I'll just do the kind of ending the events stuff, but people can keep working on the thing.
Yep.
So thank you, Josiah.
Yep.
And as mentioned, we're going to get food after this, after everyone spends some time tinkering with the problem here. But just kind of summarizing what Code Soul is, we are a nonprofit company. We do have like a bank account and all that, and we use that to pay for food. So if you want to contribute to the cost of food, you can donate to that. That is on our Discord, or sorry. Yeah, it's in the presentation here somewhere. Thank you. And then you can also find how to reach Josiah on there. But yeah, and the donation information is down there. Now, do not feel obligated to donate. Also, if you do not have income right now, do not donate. Don't do that. But do be sure to scan our QR code here, especially if you're not able to finish working on the little assignment that Josiah has given us. You can always pop on the Discord and be like, hey guys, help. And we can all figure it out together. Also, it's just a nice place to hang out. It's not terribly active, but maybe you could change that. Once someone starts talking, people join in and discussion happens. It's just no one really starts topics. But yeah, again, we are a registered nonprofit. We do these events weekly, every Saturday at 6 p.m. This week was a workshop. Next week will be a social event, and then we'll go back to workshop, back to social, back and forth. So thank you, everyone, very much for coming, and hope you have a great evening. Okay, bye, Internet. If I can find, there we go.